Hello.
Hi. Yeah, konnichiwa. I'm James from Oxford and Lisa, and this is Matt from Imperial. And yeah, it's really exciting to be here. We've already had a range of really great talks today. Looking forward to the posters after this, and of course, talks tomorrow. Also want to thank, obviously, all the organisers of this conference and Japan itself for being such a wonderful country. Myself, Matt, and Molly have spent the last 10 days sort of travelling around, and it's just been such a delightful trip. But yeah, on to what we're on to talk to you all about today. We're going to talk about how causality can help formalise a variety of concepts in AI safety. So yeah, we're here on behalf of the Causal Incentives Working Group, which is a cross-institutional collection of researchers, both in industry and in academia, led by Tom Everett, who's at Google DeepMind, and our website, causalincentives.com, kind of provides a number of papers that we've written and various tutorials and blog posts expanding on these. Some of the topics that we're going to talk about today, but also a range of other topics as well. Yeah, so I'm going to start by introducing our causal framework, and then I'll illustrate one example of how causality can help illuminate problems and solutions in AI safety. After that, Matt's going to go a bit deeper and talk about agency and generalisation, which are both kind of very fundamental concepts for AI safety. So what's our motivation here? Well, all of us are at this conference because we think we ought to take extreme risks from AI systems really seriously. And there are many different risks that people are kind of concerned about, and yet the whole field of AI safety is very new. So there's a number of concepts that kind of people use colloquially, such as agency, deception, intent, harm, etc. And these broadly actually still remain quite fuzzy and imprecise concepts. And yet if we actually want to build meaningful evaluations of AI systems, like an agency or a deception detector, it really matters that this concept captures what we really care about. And causality, sort of mostly introduced by Judea Pearl in kind of the late 1990s, and he won the Turing Award partly for this. Causality can help provide a language that does this, as it underpins many concepts of importance, as shown by this tree here. And many of these are really kind of quite intimately related to the problems we care about in AI safety. So as Matt will discuss later, we argue that agency itself is a causal concept, as it's about goals driving behavior. And moreover, we want agents to influence the world in good ways rather than good ones. And we want agents that respond to our commands as we intend, and we want agents that generalize to outside their training environment to new environments in safe ways. So what do we mean by causality? Well, we adopt an interventionist account, so this means that an event causally influences some other event if an external intervention on the first event would lead to a change in the second. So that's a bit of a mouthful, but this can all be made explicit with a directed graph, as shown here. So here we've got kind of Mr. Jones is deciding whether to turn their sprinkler on or off, depending on what the weather is outside, because what they care about is the grass being green. And so an edge from the weather to the sprinkler means that if I intervene externally on the weather, so force it to be rain or something, then we might expect that Mr. Jones would change their policy for that whether the sprinkler is on or off. And the graph itself only kind of represents which variables influence which others. So to specify the exact relationships, it's common to use conditional probability distributions. And then if you multiply these together, you get a joint distribution over all the variables, just like a normal Bayesian network. So what makes this causal is that the arrows actually faithfully represent causal relationships. So let's now consider how we model agents. So agency is central to our research for two reasons. So first, we want to understand artificial agents, and that's because it's artificial agents that are especially dangerous for a number of reasons that people are familiar with in AI safety. And yet there's lots of economic incentives to want to create these systems. And what I mean by an agent is something like coherently pursuing long-term goals, right? So that's the first reason. And the second reason, and kind of relates slightly to the previous talk, is that agency, at least from our perspective, seems to be something that we want to preserve, both individually and collectively for humanity and humans. And so we aim to understand in some unified framework how both these like artificial agents and human agents influence one another. So let's just like add a bit of notation so this makes it clear. So now decision nodes, so this is the degrees of freedom by which like an agent is choosing things. It's just giving me a square node on our causal graph. And then goals, so here the grass being green, that's going to be represented by diamonds. And then information edges, we're going to make dotted. So anything going into a decision node is dotted. So this just represents the variables in an environment that a decision maker is using to decide on their policy. And like before, the exact relationships are specified by conditional probability distributions. And the only difference with a normal causal Bayesian network is that now it's agents that decide on the distributions for their decision nodes. If you want to reason about counterfactuals, and what I mean by that is something like, okay, given that Mr. Jones uses an umbrella when it's raining, when it's sunny, would they have taken their umbrella with them or something? Like these counterfactual questions come up quite frequently. Then you actually need some extra constraints on this model, and it becomes a structural causal inference model, which is, for those familiar with causality, a structural causal model where now the agent chooses the structural function for the decision node. And formal details about all of this are listed in these papers on the right, where we also lay out theory for handling multiple decisions and multiple agents interacting. Okay, so that was kind of like the kind of background of kind of the framework we're using for a lot of these things. So now let's turn to an application. Well, some kind of safety problems relate to the causal influence of a decision on delicate variables in an environment. So, for example, will a robot damage a vase in the room? Or will an AI system interfere with the safety apparatus that's been installed? Or perhaps, will a recommender system shape a user's preferences? So how can these problems be defined and addressed? Well, let's build a toy example around that third scenario. So suppose there's an AI system that selects some content to see to show users. The content is evaluated with respect to some reward function, R, and let's just assume this is up votes or down votes from some human user or users. But to make things interesting, the human's preferences, H, can be shaped by the content. So in this scenario, there are two causal pathways by which the content recommender can influence what reward it receives. The first is to tune the content to the human preferences directly. So this is the blue edge here. This is like the desired pathway. But the second is to alter the human's preferences to make it more easily, make the human more easily satisfiable, so then it can get more reward through that pathway. And of course, that's like an undesirable pathway, so we don't want that red edge. So that's the intuitive explanation. Like we've got these two possible pathways. So can we be more formal about what is going on? Well, the first part here is that the agent can control H, the human's preferences, and achieve some specific preferences, H subscript C. The second part is that the setting of H is instrumental for achieving reward. It can change the reward, meaning it can change the reward obtained by an optimal policy. Okay? So putting these together, if setting H to some achievable value, HC, so some setting of preferences, affects the reward, then the recommender is achieving reward via the red pathway. And if the optimal policy here achieves this brings about this effect, we will say that there's an instrumental control incentive on H, the human's preferences. And intuitively, an instrumental control incentive can be understood as follows. If the agent gets to choose its policy to influence some variable X independently of how its decision influences other aspects of the environment, would that choice matter? If it does, it's got an instrumental control incentive. If not, it's fine. There's no instrumental control incentive. So, oh, sorry, I missed the thing. But we would like to evaluate these incentives just using the graphical structure of a causal graph alone. Right? We don't want to be computing these values all the time. So it actually turns out that if there is a path from the decision to the reward that passes through the human preferences here, so that this mediates that pathway, then an instrumental control incentive is possible. And in this graph, the red directed path shows such an edge. So this means there does exist data generating processes compatible with this causal graph, where there is an instrumental control incentive for the human's preferences. So that's a characterization of the problem that we've illuminated through kind of this causal graph. So now let's consider two possible solutions. The first, like we've got here, impact measures, is to apply a penalty term to any changes in the human's preferences. So this idea is being called an impact measure because it incentivizes an AI system not to impact the human's preferences too much. Of course, in order to define an impact measure, you're going to need some sort of baseline to compare these preferences to. So assume we know what preferences the human will have if they're given safe content or no content at all. We consider how similar the actual preferences are to the preferences given the safe content. And we add a penalty to the recommender's reward function that scales with the size of that difference. Well, we can see that to calculate and penalize impact in this way, the AI system needs to have a model of how content will shape the human's preferences. And the paper by Carroll and Hadfield-Medal talks about how this kind of model can be learned and used. But notice here that controlling the human's preferences is still instrumental for the AI system here. It does mediate that pathway from the decision to the reward. It's just that now the AI is incentivized to keep the human's preferences unchanged. In some situations, however, we actually want to remove the instrumental control incentives completely. That would mean that the agent is indifferent to the user's preferences and allows those preferences to evolve over time. Intuitively, the agent should choose the policy that would perform best if the human's preferences were fixed. It should consider influence along the direct causal pathway to reward, and not the indirect pathway that goes through the preferences. That was the red one versus the blue one. To do that, again, we need some baseline human preferences that humans would have if given safe content or no content or whatever. And we compute whether the human would approve of the actual content and those fixed preferences. Now, as you can see from the graph here, the causal graph, the human's preferences no longer mediate the system's attainment of reward. So the instrumental control incentive has been removed, and likewise, the intent to change the human's preferences. And this approach is called a path-specific objective, laid out in this paper by Seb Farquhar et al. And why it's called that is because it replaces the utility with a path-specific effect. So in general, the impact measure approach to this problem will tell the agent to try to keep the delicate variable unchanged, whereas path-specific objectives tell the agent to ignore any influence that it might have through the delicate variable. So it's a path-specific effect. So what I've done here is set out the general framework and then given an example of a problem that both the problem itself and two possible solutions are kind of illustrated and unpacked more by using causal graphs. Now Matt's going to talk more about both agency and generalization. Yeah, so I'm going to talk about two more recent research directions that we've been interested in.
One is about agency, and one is about generalization, and in particular, the relationship of generalization with the question of whether and to what extent we should expect our AI systems to think about the world in a causal way. And in some sense, these are like two fundamental assumptions of a lot of the previous causal incentives work, including the path-specific objective stuff that James was just talking about. So the first being that we know how to carve the world up into the interactions between different agents, that we have decision variables and utility variables in our model rather than just a causal model. And the other being that it makes sense to conceive of these agents thinking about the world in a causal way. So that when we look at the causal model and we see that this agent has an incentive to do so-and-so because of the causal structure, that this reflects something in the agent's cognition as well. And these are two pieces of work which, in some sense, investigate these assumptions. So the first one about agency, the way we came onto this is by thinking about if we have a causal Bayesian network and we don't necessarily know which variables in it are controlled by agents, how can we figure that out? How can we turn a causal Bayesian network into a causal influence diagram in order to apply some of these ideas? But this brought us onto a broader question, which is like, what is an agent in general? Which is a question that many people in many different fields have thought about before. So I think people broadly agree that an agent is like some system which pursues a goal. But in terms of how we should think about it formally, many different people have many different ideas. And in fact, I've spoken to people already at this conference who have very different ideas to us about what makes something an agent. But I'm going to talk about our answer to that question, or our first attempt at an answer to that question, in our relatively narrow realm of causal influence diagrams. But I hope that the core idea might have some relevance beyond that. So just to give an idea of the breadth of the sort of systems that I'm thinking about here, here's a selection of different types of agents. So from the humble thermostat, that in some sense the simplest possible agent, trying to keep the temperature of a room at a particular value and turning the heater on and off in order to do that. All the way up to sophisticated agents like humans, or even composite agents like a football team or a government, which consist of many sub-agents. What do all of these systems have in common? I'm going to go through our basic picture of what we think the answer is. So first and foremost, this one's quite obvious. An agent needs some ability to make a choice. There needs to be some aspect of the system which can go one way or another. We call this degrees of freedom. So Mr. Jones can turn the sprinkler on or off. The second thing, also quite obvious, this decision, this variable, needs to affect something else in our model. So here, whether or not Mr. Jones turns the sprinkler on, or how often he turns it on, affects how green the grass is. And as you might expect, we can model that just with an ordinary causal edge. The behavior causes some outcome. Okay, but the next bit is the bit which is the important part and is a bit more subtle. Our idea is that agents do things for a reason. So it's not just that Mr. Jones happens to turn the sprinkler on and this happens to cause the grass to stay green. It's that, in some sense, he turns the sprinkler on because he wants the grass to stay green. There's some kind of reverse causality where the anticipated outcomes cause the behavior. And our idea for how to model this is to consider making an intervention on the type of grass in this particular example. So suppose we made an intervention to replace the grass with some grass that needed twice as much water. If Mr. Jones is like a reasonable agent, you'd expect him to now turn the sprinkler on more often in order to keep the grass green regardless. Whereas if the sprinkler is just controlled by some fixed mechanism, then you might expect it to not come on any more often and the grass would turn brown. So the way we model this is by adding an extra variable that represents the type of grass and an extra variable that represents the sprinkler policy. Then we can imagine doing an intervention on the type of grass and this affecting the sprinkler policy. And this is meant to capture the idea that an agent's behavior is driven by its effects. And you'll notice that the arrow of causality goes the opposite way in between these type of grass and sprinkler policy variables than it does in between the sprinkler and the grass. Generalizing this a bit, we can define a new type of causal model which is meant to capture this idea. So given any arbitrary causal model, causal Bayesian network, we can add these things called mechanism variables to every variable. So each variable gets a corresponding mechanism variable, and the mechanism variable sets the conditional probability distribution of the object level variable. So here, the sprinkler mechanism is a variable which represents the probability distribution of the sprinkler being on. The grass mechanism is a variable which represents the way that the grass variable depends on the sprinkler variable. And given this extended notion of what a causal model is, we can then suggest a causal discovery algorithm for identifying agents in our model based on this idea of outcomes driving behavior. So we had this paper called Discovering Agents where we proposed an algorithm of which the core idea is basically when the mechanism of one variable responds to changes in the mechanism of another, so change in the type of grass affects the sprinkler policy, but stops responding when the causal link between them is blocked. So you can imagine here that, say, we cover the grass with a sheet of plastic so that how often the sprinkler comes on no longer affects the grass. Then we expect Mr. Jones to stop changing his policy when we change the type of grass because it's pointless now. So when we have both of these conditions, we say that we've discovered an agent in the causal influence diagram, in the causal Bayesian network, and we turn it into a causal influence diagram. So the mechanism which depends on some other mechanism turns into a decision variable, and the mechanism it depends on turns into a utility variable, or something that mediates between the decision and the utility variable. And then we have some theorem which says that at least in the relatively narrow setting of interactions between game theoretic agents represented in a causal way, that this correctly distinguishes between decision variables and other variables. Now that is quite an idealized setting, and the extent to which this procedure makes sense and is a good thing to do outside of that setting is a thing which is still up for debate. But I think the core idea is a good one. So I really like this idea of agency as outcomes causing behavior in some sense. It's like that kind of reverse causality. I think that does get at something core about what agency is about. But there are some limitations of this approach. So in particular, this distinction between mechanism variables and object level variables is a bit hand-wavy. Like there are settings where it's quite clear and natural what it is. Like you can think of like a simple machine learning setting where like the mechanism variables is like the policy of an agent, and object level variables is like its actions, and mechanism variables for the environment changing. But in general, it's not actually that clear what to do. And like when you come to try and apply it in practice, you end up having like philosophical debate about what's a mechanism, what's an object level. And it's also a very strong notion of agency, this discovering agents thing, because it assumes agents respond to things optimally. And it has a binary notion of whether they're an agent or not based on whether they do. And so it's difficult to apply in practice for all of these reasons, and also because the algorithm is quite inefficient. But I don't think that any of those limitations are fundamental. And I think we can do this idea of agency as behavior being driven by its consequences without having any of these limitations. And that's something that we're currently working on. And if anybody wants to talk more about that, come and find me later. OK, so going to move on to the other part of this talk, which is about generalization and its relationship with agents learning a causal model. So the question of whether AI systems in practice learn causal models is quite important for the kind of work that we've been thinking about in the causal incentives group. If you consider the path-specific objectives idea that James talked about earlier, this can be a bit difficult to apply in practice. So if we have a causal model of the environment, then we can apply it. But in practice, like in a machine learning context, we don't necessarily have a causal model of the environment. We just train some system to perform well in an environment. If the system has a causal model explicitly built in, then we can tell it, with respect to its own model, it's OK to influence this variable via this path and not via this other one. But at the other extreme, like if the AI systems that we have don't even think in a causal way at all, then it seems like it would be very hard to implement these ideas like path-specific objectives. But if the reality is somewhere in between, where we don't explicitly build in causal knowledge to our systems, but they learn it anyway, then it might still be possible to communicate to them that there are acceptable paths of optimization and unacceptable paths, for example. And so this part of the talk is about a recent paper investigating this by John Richards and Tom Everett in the group, which investigates the relationship between a system's ability to generalize out of distribution and whether it's learned a causal model. So just a quick overview of what I mean by generalization. We'll go through it in a simple example. So suppose we have a classifier, an image classifier that's trained to classify pictures of dogs and pictures of wolves. So in some sense, you could think of this as like a very, very simple agent. So we show it lots of images in training, and then at test time, we give it new images that it hasn't seen before. We want it to generalize to correctly classify these new images. One type of generalization is within distribution generalization. So suppose that at training time, we always showed it pictures of dogs on grassy backgrounds and wolves on snowy backgrounds. And then at test time, we give it a new picture of a dog on a grassy background. This is like testing its within distribution generalization. But if we give it a picture of a dog on a snowy background, then this is not just a new image, but it's a new type of image. It's like fundamentally different to what it's seen before. And so we're testing here out of distribution generalization. In distribution generalization is something that neural networks do very, very well, and it's fairly well understood. Out of distribution generalization is harder and less well understood. But we can think about it in a causal way. And the way that we can do that is by modeling the data generating process as a causal Bayesian network. So you can imagine that this picture of a dog was generated using two latent variables, one of which representing the type of animal, dog or wolf, and one of which representing the type of background, grass or snow. And these two variables are highly correlated, at least in the training distribution, because they're both caused by another variable, location. So warm locations have dogs and grass, usually. Cold locations have wolves and snow. And the true label of the image depends only on the type of animal, not on the type of background. Now, we can model a distributional shift via an intervention in this causal model. So you can imagine that we reach into the causal model and we change this background variable so that some backgrounds which were grassy are now snowy. This corresponds to the distributional shift that we were thinking about. Now, it should be fairly clear that if you have a causal model of a decision problem, this is very useful for generalizing under distributional shifts. Because we can look at this and we can see that, okay, the true label doesn't depend on the background variable. If somebody intervenes on the background variable, we just continue to classify according to the type of animal. That's pretty useful. So causal models are sufficient for out of distribution generalization. But the question we're interested in here is whether they're necessary. So does any system which successfully generalizes out of distribution need a causal model? And some version of this question is like often debated in machine learning. So on the one hand, causal models are very useful for generalization. Lots of people are excited about causality. But on the other hand, learning causal models explicitly is very hard. Like the number of causal Bayesian networks over a set of variables is like enormous, and it's very difficult to do causal learning. And also, state-of-the-art AI systems don't seem to need causality. At least they don't have it explicitly built in. So here, this is Gatto, the DeepMind decision transformer agent from a couple of years ago that did very good, learned successfully to complete lots of different tasks and did some out-of-distribution generalization, but has no causal model built in. And seemingly, the people who built the system weren't thinking much about causality at all. And at least on the surface, it would seem that lots of systems like this are trained with purely observational data. But the result that we're going for here is to show that such systems, even if they don't have causal models explicitly built in, they must have learned them implicitly to the extent that they can generalize out of distribution. But to get to that, we need to formalize the problem a bit more. So this is a bit of a toy formalization of the generalization problem. You can decide for yourself how good you think it is. But yeah, the way it's modeled in this paper is that we make some intervention to get a distributional shift, sigma. And we also tell the system what intervention we've made. So we say, we've made distributional shift sigma. Now, we don't give it a causal model. We don't tell it what that distributional shift means, but we just give it some regime indicator which tells it the distributional shift has taken place. And the reason we do that is so that we can model the system having a policy which explicitly depends on distributional shifts, so that in theory it could respond completely optimally with respect to every distributional shift. Now, obviously, this is not how generalization works in the real world. You don't necessarily get explicitly told what distributional shift has taken place when it does. But I think it's a reasonable formalization, mostly because it actually makes the generalization task easier than it is in practice, because you're told what distributional shift takes place. So if we can prove results about what's necessary to complete this task, then that suggests it's necessary to complete the harder task of actual generalization. And in particular, we consider the entire set of possible distributional shifts on the data generating process. And we look at the worst case regret across that set. So we look at what's the distributional shift for which the system, there's the biggest gap between how well the system performed and how well it could have performed. And then, indeed, you can get this result, which says that if a system successfully generalizes across all distributional shifts on a set of variables, then you can infer the causal Bayesian network over the data generating process from its policy. So this doesn't necessarily mean that it is explicitly thinking in a causal way, although it's kind of unclear what that sentence means, really. But this means that you can, just by looking at the way it changes its behavior when you make a distributional shift, you can infer the whole causal model. So all the causal information is present in its policy, and you can use its policy to answer causal queries if you want. You don't need to be able to see the outcomes of these latent variables. You do need to know what variables are being considered. And there's also an approximate version of this result, which says that if a system if you have some regret bound on the system's generalization error across distributional shifts, then you can also get a bound on how good an approximate CBN you can get from their policy. And yeah, here's some data from a toy experiment showing that lower regret bound gets us a lower error rate on the learned DAG. Okay, so what are the consequences? Well, this would seem to suggest that to the extent that systems like language models, which don't have explicit causal models built in, can nonetheless generalize under distributional shifts, which they can to some extent, they must be learning causal models of the environment, even if it's not explicit. And this happens if you give a system a sufficiently rich training distribution, which covers sort of many different distributional shifts on some simpler distribution. Another consequence is that if you can't infer the correct causal graph from the data, then it's impossible to generalize always, which has relevance to questions like goal misgeneralization, which is a failure mode of AI alignment. But the consequence that I want to think a bit more about here, which you could call a conjecture really, is that this suggests that agents that generalize well should be able to understand and implement the causal concepts that we've been thinking about, like path-specific objectives. So the really naive version of this is that you could say, well, if a language model generalizes well under distributional shifts, it must understand causally what's going on, so we could just try telling it, optimize this variable through this acceptable path and not through this other unacceptable path. And that's something which maybe might work, but also just may well not work. But there may be more sophisticated things that we can do in order to infer the causal model that a system is using in a particular context, make interventions on that causal model in order to train it to optimize variables through some paths and not through some other paths. Yeah, so to conclude, this has just been a snapshot of a few different things that we've worked on in the causal incentives group, but we have loads more papers basically on the theme of applying these Perl causality ideas to different AI safety problems. Which includes all of these things, so decision theory, agent incentives, deception, corrigibility, fairness. And if you're interested in any of those things, you can find all of the papers at our website, causalincentives.com. There's also a blog post sequence which we wrote last year trying to give it a fairly accessible introduction to a lot of these ideas. You can also find that linked at causalincentives.com. We also have a Python library, PySid, for working with causal influence diagrams, again, linked at causalincentives.com. And you can use this QR code if you want to get there. And the final thing I want to say is that we also have like a bi-weekly meeting, the Causal Incentives group, like Tuesday afternoons, UK time, online, where people present what they're working on, and we often have people come in and present their work if it's at the intersection between AI safety and causality. So if anybody has work that is in that intersection and wants to come and present it in the group, or just wants to come and listen to us present stuff, then email me or James, and we can make that happen. Thanks. Any questions?
You need to hold it down.
Thanks.
All right, any questions? Perhaps from the right-hand side of the room, who have been pretty quiet so far? We'll take one from Manuel while we wait.
Well, thanks for the talk. I got a question, I guess, first for James. I'm thinking about the two solutions that you presented right before Matt started. And I think I have some bias, like in thinking of the second solution as like, the best one. Because we are cutting that edge, like in that causal graph, there can be no causal incentive driven by. And it feels like, the first one is more like, something that will work well for practical implementations where you have like some function with two objectives and then you do like multi-objective optimization. Is this bias something I should throw away, or is this something that actually happens in practice?
My bias is the same way. So it's, I guess, hard for me to defend the other approach because I naturally think that, there are some advantages. To recap, this was the impact measure approach where you're kind of penalizing changes to human preferences in that example. Although I introduced these two solutions in the context of content recommender, that was because it was the simplest example that just has like a really simple graph. And so, but like this applies like very broadly to many different setups, right? But that's like a penalty on the reward function. And then the other one is like, okay, you want the AI system to optimize along certain causal pathways and not along others. And the latter seems like, much more more useful, but it actually links to what Matt was talking about in generalization, because the implicit assumption here is that like what is like the causal structure of the world, and B, like the AI system does. And like, is that like a fair assumption to make? Well, the generalization stuff is implying that perhaps it is, yes. But again, you have these differences between what is the causal model that it's learned and what's the causal model that you think is true, and what is the objectively true causal structure of the universe. And those, again, affect like that path-specific effects. Does that make sense of it? Yeah.
Other questions? Let's go for the back left corner.
Thanks for the talk. Really interesting. I guess just coming back to what you just said about we develop these causal structures of the world, and these AI models do as well. But in real life and research, it's very difficult to infer these causal structures of the world. It's the problem of correlation versus causation, and then you have a whole bunch of confounders that perhaps the AI model hasn't confronted yet, or just is not aware of. I suppose, how good do you expect these systems to be at sort of discovering these possible flaws, perhaps having some sort of uncertainty metric around whether there could be confounders or they're just lacking proper causal structure?
Yeah, it's a great question. Do you want to answer that?
So is the question like, how confident can we be about the causal models that we obtain in order to try and apply some of these ideas? Do you want to clarify if that's a misunderstanding?
That's pretty much it. I guess just how well can these systems generalize without complete knowledge of the causal structure of the world? Right.
So, I guess the situation is that we have systems that we know can generalize well, and what we know less is the extent to which they think in a causal way. And some of this work is just trying to kind of get at that, make a start on that, and try and establish, like, is it the case that generalization is just a function of causal understanding, and that, like, the extent to which something can generalize is the extent to which that it has causal understanding? And I think that's, like, a question that's starting to be answered, but is still, up for grabs. And so, I think all of these questions about the relationship between generalization and causality, and like how well you can generalize given some causal understanding and how much causal understanding you need for a certain amount of generalization, are pretty open. I don't know if I have a great answer on that.
Yeah, the question on tractability of this approach, right? So I think it's like, like most theoretical approaches, you start with really easy examples, and then you like hope that this can like go further. And it's correct, like in causal discovery, you have these guarantees that if the like data is in certain ways, then it requires this much interventional data in these different settings to be actually able to faithfully learn the causal graph. And those are quite like worrying like results, whatever. But I think my response would be that like you don't necessarily need to know the full causal structure of the environment. Like I don't actually need to know when I'm acting as an agent, like how all these atoms are interacting with one another in the floor or something, and like I don't know, like lots of things about this room. Instead, I'm doing this kind of what I'm alluding to here is sort of this causal abstraction work and causal representation learning and things, where like actually there's kind of like just this higher level features, which means you don't need to know as much as you think you need to know about the environment in order to be able to like make useful predictions about the system's behavior. Actually, probably when I'm making decisions about my policy, I probably only need like some small set of variables to be able to make those predictions. But that's conjecture. But yeah, maybe we'll talk about it afterwards.
Keep your hand raised while the... Thank you.
Thank you for the talk. Regarding this second solution, hypothetical preferences under safe content. It's something that's probably difficult to collect data to create model, or I don't know, some limits. Just if you can say a few words.
No, it's a good question. Basically, in order to come up with any kind of either of these approaches, you need some baseline to compare to. You need something that like you think is like the good preferences or whatever, the ones that you care about. And we're not wedded to any particular thing here. This could be like no preferences at all. It could be like preferences under some sort of safe content. It could be like a host of different things, like the previous speaker was talking about in terms of moral graphs and things. Like there's a host of different things that you might wish to like retain or care about from a preference perspective or values or anything. The important part here is like there is some baseline that you're comparing to, and both these kind of things, the actual content and like wherever the thing you think is like the safe thing that you care about, both like have causal pathways to this reward function here. But kind of like substitute whatever your like pet thing is for that node. Sorry, I can't point to it, but for like what you think is good preferences or like things that we care about. Does that make sense? Yeah, it's not wedded to that.
Thank you for the talk. It seems like a lot of the work is about kind of finding agents, characterizing agents. You know, your latest paper I was reading is ascribing intentions to language models. I'm curious if this work has any bearing on what to do next, right? Okay, you found out that it's an agent. Do you want to make it less agenty? Do you want to make it less agent or the same amount of agenty but in a less dangerous way? Have you thought about that?
Great question, yeah. So I mean, the starting motivation, as I put on with the tree picture, was like, right, okay, if we, well, at least one motivation is like, okay, as all of these people coming up with evals and like measurements and whatever, that's brilliant, that's great. But are these actually like measuring something that we care about and is like the thing we like want to preserve or like not have or whatever? Or is it just some arbitrary number that's not actually grounded in something that is meaningful? And so the starting thing at least is like, okay, let's actually, like the intention work, for instance, or deception or like agency, etc., is like, let's actually formalize like what is the concept we care about. The second thing is, and Matt's working on this at the moment, is like, okay, can we now use this to like motivate the construction of evals that like are actually grounded in something like that captures this, and not just us. Like maybe my expertise is like more theoretical, but like collaborating with people that have those other, you can go, okay, well this is like what you actually care about, this concept. Now can you make like some sort of test to like check for this? Yeah, does Matt want to expand on that?
Yeah, I think that's a good answer. I mean, some like more specific things is like you might want to know like where in your ML model that you've trained like the agency part lives, like where are goals represented in the model, and where does like the decision to try and influence a variable in a certain way happen. And these seem like things that you can do using some of these ideas to try and identify like where is the agentic part happening. I mean, like a neural network is a causal graph in a sense, and so figuring out where goals are represented in these models and where like decisions take place is like one possible application.
Okay, we have time for one more, and Andre has had his hand raised for the and keep it raised, please, while the microphone comes to you. Thank you.
Thank you very much for giving me the last question, and thank you for your talk. I have a question which may sound like the previous one, but let me first give you an example that would simplify the understanding of what I mean. Could you please go to the slide with the dog?
Go to what?
To the slide with the dog when we classifying dogs and wolves, or just dogs. Yeah, so imagine here we have an agent which is trying to classify just flags, and we have two flags, one of Monaco and one of Indonesia. They actually have the very same flags, red and white strip. And if we just looking at them, it's hard for us to say what the flag is. But if we had a woman in hijab with a very sunny weather who is holding this flag, for a neural network, it would be much simpler because the context would provide us a lot of correlations. It's not a casual thing because obviously she may hold a Monaco flag, but in most of the cases she would be holding Indonesian flag. And in these terms, why I was giving this example, because you have illustrated that casual reasoning can help us to avoid features that are not relevant, but actually this information about that the background is not relevant for classification task is not that obvious, it's not that always. And for dogs, actually, there may be example when the front is more important for classification because it would provide some additional features that the only image of the dog is not capable of. And to distinguish if we can don't think about background or not, we, of course, can do this, but just adding more data. And in these terms, for me, it's not that really obvious that we can add more data to understand when we can build a casual model and skipping off background, or we can just put more data to learn more about dogs on snow. So for this thing, that trade-off is not clear for me. Could you please elaborate?
Yeah, so I think it's a really good question. Like sometimes these like associational but not causal heuristics are like very, very useful and might be, a lot of the information you use in order to do a classification. I think that question is kind of why people were thinking about this kind of research direction, because when you think about it like that, it seems like, maybe generalization comes from just having more and more such heuristics, so that like when one of those heuristics fails, you've got other heuristics too that you can use as well. So like if like the weather is like really bad in one place where it's usually good, you can fall back on other heuristics. And it does, that is a completely plausible way things could happen. But then it's also plausible that the reason that you get better generalization from more and more data is because you start inferring causal properties from the data as well. And so I think, that's the exact sort of question this work was trying to investigate. And I guess in some like limited formal sense, we show that the answer is that, you need the causal knowledge for like really, really good generalization. But like in practice, the extent to which that applies in practice, like are we actually reaching that point with our models where they actually need causal knowledge, or are they still getting most of their success out of like better and better heuristics is, I think, still an open question.
But of course, heuristics themselves could be represented in this framework as just you having different variables for each of your heuristics, which like are parents of your decision, whatever.
But it wouldn't necessarily need to be causal.
It wouldn't need to be causal, sure, yeah.
Okay.
So thank you very much.
Well, on that note, thank you very much, Matt and James.
Thank you.
And let's draw this thing to a close. I have a couple of minor procedural notes as